It is my pleasure to introduce Kevin Schwiers. Kevin has been an IT education instructor for over 15 years. He has over 35 years of computer networking experience and currently holds the CCNA routing and switching and CCNP data center certifications. Kevin, it's all you.
Okay, good afternoon, and thank you for the opportunity to communicate with you this day. We're going to talk about segmentation regarding Ethernet segmentation within a LAN. And I'm going to use the OSI model. Now, I have heard some arguments, OSI is dead, why use the OSI? I really don't care one way or the other, but I can share with you that when I went to Cisco Live, I asked every single vendor, 100%, every vendor, I was on a mission to describe their product, and 100% used the OSI to promote their product. So we'll leave that at this, leave this at that, and go forward. All right, so there's two terms that I want you to invest in, and if you take my classes, you know I'm pretty hard about this, and that is collision domain, or also known as contention domain, which has to do with when is it my turn to transmit. Ethernet is chaotic. It was designed that way. It's like a party line. You listen, and if nobody's talking or transmitting, then you transmit. But it's understood that it is a shared medium. So therefore, we have protocols like CSMA, Carrier Sense Multi-Access, which says listen before you speak. And then we also have another protocol known as collision detection, which says if there's a collision, hush up for some amount of time and try again. You might compare this to at that time in the 90s, token ring, token passing, which was deterministic. We knew who was going to have the token and when. Broadcast domain is simply how far my broadcast, which is a destination address intended for everyone who can hear it, how far it will go. Domain. Okay. I'll be, sure enough, thank you. Okay, so let's start with an Ethernet frame. So we have a preamble, which is used for synchronization and timing, and directly behind the preamble is a destination address of 6 bytes, followed by a source address of 6 bytes, the type or length field, depending on what we're discussing, and the data, which could be anywhere from 46 to 1500, and then a frame check sequence to ensure you receive what I intended you to receive. If we go with the smallest data field, you'll see that we have 64 bytes. In Ethernet, nothing less than 64. That's the smallest accepted Ethernet frame. And then if you use the upper range 1500, we have 1518. And so if I do receive a frame less than 64, it's known as a runt. If it's greater than 1518 but less than 1600, you test takers, Cisco calls it a baby giant. So we're going to end at layer 1, the physical layer. There's no segmentation. It's referred to as a flat network because all ports participate in one common collision domain and one common broadcast domain. You call these devices repeaters or hubs. So when a frame is received, it's simply repeated out all ports. We use it to give greater distance, or back in the early 90s, we used it for expansion. But the problem was computers got faster, we had more participants, and it just couldn't hold up to the contention. So we needed something to help us. So we moved up to layer 2. A layer 2, you test takers, if you're familiar with the Cisco certifications, creates multiple smaller collision domains, but out of the box, still all ports share one common broadcast domain. Some of you might know outside of Cisco that layer 2 is called a hub, but more explicitly an intelligent hub because it can make forwarding decisions on hardware addresses. Examples of hardware addresses are MAC addresses. Back in the day, I can remember jumpers, dip switches, etc. We also have VLANs, virtual LANs, where we logically divide up the physical device. Each VLAN behaves like its own separate layer 2 device, own separate bridge or switch. Bridge is often used to generically imply layer 2. So VLANs give me segmentation, security, and network flexibility without having to rerun cables. Without VLANs, you control broadcast domains with routers. It's up to you, the administrator, to create knowledge of the VLAN on each switch and then allow those VLANs to propagate across either access port or trunk. It's up to you to align multiple VLANs so that they appear as though they're one single VLAN. In that appearance, they're actually one common broadcast domain. And we know that each unique broadcast domain should map to a unique network. So if I have my Ethernet frame directly behind the preamble's destination MAC, followed by source, this frame is received by a switch. The switch will inspect the destination MAC to see if it truly owns this frame. Do I own the destination MAC address like Cisco Discovery Protocol, Spanning Tree Protocol, VDP, DDP, etc.? If the answer is yes, we discard layer 2, and now we have to inspect layer 3 because it might be ping, telnet, traceroute. Normally, this is what we call the management VLAN. The management VLAN is where the switch is accessible as a host. So if the MAC address does not belong to the switch, well, then the source MAC address will be played in the MAC address table, placed in there for 300 seconds, also known as 5 minutes. We will then look up the destination MAC address. When we do, we look for an exact match, meaning all 48 bits or all 6 bytes or all 12 hexadecimal characters have to match, else flood. A layer 2 switch can only make one of 2 decisions. It can say I can filter, meaning I have a match, I will forward it out that port only, or flood, which means I don't have a match, I will forward the frame out all ports except for the port in which it arrived of the same VLAN. When you create VLANs, it's as if you have multiple unique MAC address tables. So flood or filter are the only 2 decisions. We started at layer 2 using bridges years ago with coax cables. Therefore, they were shared segments, and you could have multiple source MACs tied to individual physical ports. Back in this time frame, all ports had to be the same speed. It was software based, which means it has to go to the processor. Didn't scale well. So then we started bringing in what we know today to be the switch. All right, so here I have a host MAC address and a destination host MAC address, source and destination. Okay, remember directly behind the preamble is the destination that's unique to layer 2. So as this frame arrives on physical port 1 on a switch, we're going to populate the MAC address table with the source MAC. And because that port belongs to VLAN 10, we're only going to question ports that belong to VLAN 10. Remember, each VLAN behaves like a separate physical device. We don't have a match, therefore we flood, which simply means for the frame out all ports except for the port in which it arrived. In my scenario, the destination I'm looking for is physically connected to port 7, so it's going to receive this, and it's going to respond back. Now, when we respond back, it's going to enter port 7. We're going to learn the source MAC address. We're going to seek the destination. In this story, we have knowledge of the destination. So therefore, we're going to filter. And the definition of filter is to forward the frame out that port only. Your device, your switch, can make a decision either after receiving the destination MAC or after the first 64 bytes or storm forward, depending on what's occurring. Now let's elevate it to layer 3 of the OSI model. These are known as routers or layer 3 switches, and in some cases they're documented as intelligent hubs, making forwarding decisions on logical addresses. Inherently, each individual interface participates in a unique collision domain and a unique broadcast domain. In the early 90s, routers were very few and they were very costly. Today, we don't think anything of adding routers, but it was significant in like 1990 through 94. Because each interface is a unique broadcast domain, it should map to a unique network address. There are some compromises to this when we use sub-interfaces, which logically divide the physical interface so that we can have multiple recipes. So when a router receives a frame, it inspects the destination MAC and it says, is it for me? And if the answer is yes, the layer 2 is discarded. Layer 2 is discarded. So then it will inspect the destination IP to see if it owns that. If so, it processes it just as a host would. If it doesn't own the layer 3, it now will challenge the route table for longest match, else discard. So a router is a brick until it has information. A switch, on the other hand, a layer 2 switch says, I will learn and I will flood. I will slowly build my table. Longest match means let's challenge the routing table for all 32 bits of the destination IP. And if I don't have a 32-bit match, then let's try 31. And if not 31, 30, 29, 28, 27, discard. Now, we as administrators may choose to put a route in there called a default. It's a match of 0. It's a way of saying if I know nothing at all, don't discard it, hand it to the next. All right, so now would be a good time to entertain questions.
Thank you, Kevin.
Okay, so my voice, go ahead.
Yeah, no, I was gonna say, I think your voice has been going out a little bit here and there, so I'm hoping everyone, it was just a few brief moments that your voice kind of went in and out, so I don't think it affected the presentation and the information, so
Okay.
don't want you to stress about that. But we don't have any questions yet in the Q&A, but I'll answer a few of the ones that I know that are gonna come up. So, yes, you will receive a copy of this presentation, a recording, about a week from today. So you can look for that. It will be sent to the email that you use to register. And also, this comes up frequently, we do not offer participation certificates for showing up. So, so that's that. And I guess if I'm seeing people raising their hands over there, but if you put your questions in the Q&A section, that would be awesome. That's where we can answer this for you. So we'll give everyone just a minute or two here to see if we have any questions come through. And here we go. How is switching and routing will change in the era of IP version 6?
Same, no difference. IP is just, IPv6 is just at layer 3. It's just a bigger, uglier address, but it's the same. No difference.
Perfect. Okay. All right. Well, if we don't have any more questions, I guess we'll move on here. Thank everyone for joining us today, and thank you, Kevin, for taking the time to do this awesome presentation for us. We truly appreciate it. Appreciate the questions. Oh, here we go. Paul Melnick is asking something here. It's in the chat. Are there any differences in all these things between vendors like Cisco, Juniper, etc.?
No, OSI layer 2 is layer 2 regardless of vendors. OSI layer 3 is layer 3 regardless of vendors.
Perfect.
There's not in what I've discussed with you. what I shared with you today would be applicable regardless of vendor.
Gotcha. And then we had a couple follow-up questions from the first question you were asked about the switching and routing and how it will change in the era of IP version 6. So what about in the cloud environment?
Well, I think it's best for me to answer that by saying I'm not armed to answer that. I'm not, yeah, I think it's best I evade that one. I'm sorry for that.
No, all of us that are married know how that goes. Sometimes you just have to sometimes it's better to answer questions.
Yeah, that's like swimming with a lead tennis shoe, and honestly, I'm just not armed.
Okay, fair enough. And he also said, what about the virtual switches and routers?
Okay, in your virtual switches and routers, the fundamentals I shared with you today are applicable. They are the same. But when we get into like layer 2 redundancy, spanning tree issues, we have better protocols that communicate more information so that we don't have the same problems that we find in the inherent behavior of like layer 2 flood. So there's what I shared with you today would still be applicable.
Perfect. Okay. Will switching and routing have a scope for automation as other sectors are moving towards it?
Automation is where we plug and play and the device is provisioned, and that the management plane is handled, and we also influence the control plane. But your automation is still going to address these fundamental ingredients. Let's remember, whether you make cinnamon rolls, whether you make a loaf of bread, or you make various flavors of bread, salt is salt, sugar is sugar, wheat is wheat. So what I've shared with you is the raw ingredients, and they're still going to be in place.
Perfect.
In Ethernet. Now, Ethernet might morph into something else. In my 36 years experience, be careful. I've learned, be careful. Whatever I brag about today, I'll be embarrassed about tomorrow. You can find other layer 2 encapsulations that do things different, but in Ethernet, what I've shared with you today is pretty much generic across all scenarios.
Gotcha. Okay. In IP version 6, will subnetting still exist?
In 1990, I'm old school. In 1990, when they were bringing out IPv6, they said no subnetting, no subnetting. It was a very nasty word. But yet, IPv6, global knowledge would be given the first 48 bits, and then they would assume global knowledge would extend those 48 bits another 16 bits, and they're actually called subnetting. What has occurred is, what does subnetting mean? The definition has changed. Back in 1990, we had class-full boundaries. We had fixed capacities, and we subnetted to evade, to break away, to move apart from those class-full boundaries. Today, subnetting just means we're taking what was previous and making it smaller. So yes, there's subnetting, absolutely. And because of classless routing, I can move my mask way beyond the 64 if I want. But it's just amazing what I witnessed from back in the old days, where that was a forbidden word, to the way that we embrace it today.
Awesome. Okay, next question for you here. Is it true that IP version 6 will end the need to NAT?
Well, that's a good argument too, that goes way back. If you go back to the 90s, the big brag of IPv6 was, remember back in 1990, the world was flat. Our networks were huge. We said we need 1,000 hosts. So back in our world of thinking in that time frame compared to today, see, back then, 80% of our traffic was logically local. Today, 80% of our traffic is logically remote. Okay, so, oh, I'm sorry, I just jumped track and forgot what I was asking. What was the question again?
No worries. So is it true that IP version 6 will end the need to NAT?
Okay, going back to NAT. So in the early 90s, it was saying end to end without NAT. You don't need NAT. Well, there's truth in that. There is truth in that. But this is 2020, and we're concerned about security issues that we did not have in 1990. So NAT is not an evil thing. And that was considered burdensome and evil in 1990. Here it is 2020, and NAT gives us a sense of security and also enables us to transition. So yes, IPv6 does not require NAT, but you as a customer may choose NAT. NAT, network address translation, in the early 90s was actually marketed as a natural firewall. It was actually marketed as a natural firewall because your inside identity was hidden from the public. So going forward, do we need NAT? No. May you choose to use NAT? That's your business.
Gotcha. Okay. What are the frequent reasons for packet drops?
That's another one, swimming with a lead tennis shoe. I'm not sure I can answer that in a timely manner.
Okay, no worries. Let's see here. Can we use Cisco SG300 manageable switch best for virtual switching?
I'm not armed on individual products like that. I'm sorry.
Gotcha. Yeah, no worries, no worries. Okay, last one here. I found it was a bit speedy, but good slides. And oh, okay, it's just a comment. All right, cool. Well, again, Kevin, appreciate you being with us today, and appreciate everyone jumping in here in the end with some really awesome questions. We appreciate going in the previous slide there. We saw if you use the code. It's webinar 25 in the US and CA webinar 25 in Canada. That'll give you 25% off your next global knowledge course. So again, we appreciate everyone being with us today. Be sure to continue to visit the Global Knowledge website where you can access additional free resources like technical articles, white papers, and fantastic webinars like this. Also, if you have more questions, reach out to our social media team, Twitter, Facebook, LinkedIn, Instagram, whatever your preference. Let's make those folks earn their paychecks. They can put you in touch with the questions you need to have answered. So again, Kevin, thank you for your time. We appreciate it. Everyone out there, stay healthy, happy, good hand washing. Good luck with all your kids at home. Have a good one, everybody.